Let me know if there's any more problems. I think it should have improved significantly. But just let me know if you are still experiencing any problems with your audio. Right. So, like I said, today we're going to be discussing or talking about truth tables for the first part of this session. And then the second part, we're going to be having the discussion on validity, right? And what we can deduce and how we come about to validity. All right. Now, let's look at truth tables. Let us look at truth tables. So we looked at truth tables for operators in the previous lesson. So what did we do? We saw what was the output of each individual operator, what was the truth output of each individual operator, right? So we did that for conjunction, for disjunction, for negation, for implication, and for if and only if. So that was the first introduction to truth tables. All right, now there's a lot more information that we can gain from these truth tables than we have known that we know to date. Right. So we know how to construct the truth table, but then what we don't know is this was just simply the beginning when we had P and Q. Right, we had P and Q, and then we drew the truth table for that. Right. So sometimes you can have a statement as long as say something like this, or well, maybe even much more bigger than this, right? So you can have a propositional logic statement in this format. Yeah. So having a propositional logic formula in this format, right? You might want to evaluate the truth output of the truth output of that formula, right? So from the behavior of the truth output of the given formula, right, we can categorize a statement into any one of these given statements, right? We'll look at each one individually, but all this we can say just by looking at the truth table. All right, this is referring to that, right? So we can speak of logical consequence, right? We can speak of logical consequence when we have a truth table. When we have a truth table and we have logical consequence, we say that. So let's look at logical consequence. When we talk of logical consequence, we talk of the fact, or when we talk of semantic entailment. Right. So what is semantic entailment, by the way? So semantic entailment is a behavior that we observe when we are given a couple of statements, say A, B, say C, right? And then we have another statement, D. So we say A, B, and C semantically entail D. A, B, C semantically entail D. Entail D. Meaning, every time that A, B, and C are all true, D should also be true. Whenever A, B, and C are all true, D should also be true. Should also be true. Right. So that is semantic entailment. So we can already observe, right? We can already observe if we were to draw a truth table. If we were to draw a truth table, say we have got P implies Q or R, right? Let's rather put it this way. Let's say we have we've got statements, right? We've got statements. We've got not P, Q, not R, right? And then we have P and Q implies R, right? So we want to find out the relation between these statements and the fourth one. So these three statements and the fourth one, right? So usually that's how the question will be structured. They're asking for the relation between the three statements with respect to the fourth one. Right. So we are going to draw this as we draw to the end of this class, right? But now we have a definition of semantic entailment. Whenever they are true, D should also be true. So it doesn't say anything about when they are false. So when they are false, right, even if it is true or false, right, if one of them is false, it can be true, it can be false, it doesn't really matter. We don't gain much information, but we are looking only for those scenarios when they are all true, and we are saying the fourth statement, whatever statement that we have, is going to be, should also be true. So now we have another definition we need to quickly look at, and that is the one for logical equivalence. So logical equivalence. So logical equivalence says, right, if you are given two statements, right, so given two statements, we say they are equivalent. We say they are equivalent if they produce an identical column in the truth table. In a truth table. If you were to draw the truth table for these two, right, their output column is going to be identical. Once we have that, we can say that the two statements are logically equivalent. Right. So you've got column C, you've got column D. If this is true, true. If this is false, false, true, 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 true. These are logically equivalent. Whilst was two, then we can draw a truth table for comparing P, Q. We have true, 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 false, false. We have true, false, true, false. And then we've got P implies Q, and let's say not P or Q. So let's have not P over here. So P implies Q is true, false, true, true. Not P is going to be false, false, true, true. Not P or Q. So true or false is true. False or false is false. True or true is true. False or true is true. So if you want to compare these two, you see that they reproduce the exact same column, output column in the truth table. So in that scenario, we can say that they are equivalent. So we can say P implies Q is logically equivalent to not P or Q. Right. So that is logical equivalence. We can also look at a tautology, right? We can also look at a tautology. So a tautology is a statement that is always true. Tautology. So this is statement always true. Statement always true. For example, we can have the statement P or not P. So if I draw the truth table for this, I'm going to have P, true, false. Then I have not P, it will be false, true. And then I'll have P or not P, true or false, true, false or true, true. Right. So the output is always going to be true here. We always have a true output. So what does that lead to? It simply means that it is called a tautology. Right. Related to this, you also have what you call a contradiction. Right. So a contradiction is something that is always false, statement always false. Statement always false. Right. So for a statement, say P and not P, right? We already have the first part of what we need. So we've got 1, 2, P, not P, P and not P. So true, false, not P is false, true. Conjunction true and false is going to be false, true and false and true is going to be false. Therefore, we have got false all the way. So that is called a contradiction. A contradiction will always have something that is all the outputs on the truth table will be false. Right. So we also have what we can call tautological equivalent. We can also have what we can call tautological equivalence. Tautological equivalence. Right. So tautological equivalence speaks to those formulas that always produce the same truth table but being tautologies. Right? So if you have true, 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 you always produce this, and another statement always produces true, 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 then we can say these two are tautologically equivalent. Right. Now there's a difference between tautological equivalence and logical equivalence. So there's a difference between logical equivalence and tautological equivalence. The difference arises from the fact that all tautological equivalences are logical equivalences. Right? So tautological equivalence, right? We can say it is a subset of logical equivalence. Right? All tautological equivalences are logical equivalences, but not all logical equivalences are tautological equivalences. So tautological equivalence is a subset of logical equivalence. So there's another thing that we can also check, right, which is called satisfiability. So under propositional logic, we say a formula is satisfiable if it evaluates to at least one true. Evaluates to at least one true. So in another way, or in other words, you can define satisfiability as to say if a formula is not a contradiction, it is satisfiable. It's not a contradiction, it is satisfiable. It is satisfiable. Right. So as long as you have a true value in its output column, we can say it is satisfiable. There is a way of getting to the truth. Right. So that is the definition for satisfiable. Right. So all of these elements we can learn from just looking at the truth table. So given a truth table of any multiple formulas, we can deduce logical equivalence, tautological equivalence, contradiction, tautology, satisfiability. Right. So that is the power of the tool called the truth table. And we should also be able to correctly draw one. So let's look at some questions. Right. They say construct a truth table for the following first order logic sentence. And write down the option giving the correct interpretation of the truth table. So you have to draw a truth table for this, right? You have to draw a truth table for this. So let's go ahead and see. So you're going to have how many inputs are there? We have A, B, and C. So you're going to have A, you're going to have B, and you're going to have C, right? And then we're also going to have, we want to construct, we're going to have node B, we're going to have node C, we're also going to have node A, and then those are the last ones. Then we're going to have B and C. We're also going to have node B or node C. Then we're going to have A implies B and C. And then lastly, we're going to have node B or node C implies node A, like that. So we've got 3 inputs. We're going to have 8 rows. So we're going to have 1, 2. So let's see. So we've got 4, 5, 6, 7, 8. Right. So there goes our truth table. So remember, if we've got n inputs, we're going to have n 2 to the power of n rows. In this case, we've got 3 inputs, so we're going to have 2 to the power of 3 rows, which is 8 rows. Right. So the innermost one, C, is going to alternate truth value at every 2 to the power of 0. That is 1, true, false, true, false, true, false, true, false. Then B, as we move out, we're going to alternate after 2 to the power of 1, true, 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 false, false, true, false, false, and then we're going to also have true, 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 false, 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 false. One. That is the first part. Now we want to give not B. Not B is the opposite of B, so it's false, false, true, true, false, false, true, true. And then not C is false, true, false, true, false, true, false, true. Then not A is false, 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 true, 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 true. Right. Then now we have got B and C. We are taking B and C. True and true there, that's true. True and false, that's false. False and true, that's false. False and false, that's false. True and true, that's true. True and false, that's false. False and true, that's false. False and false, that's false. Then not B or not C. False or false, that's false. False or true, that's true. True or false, that's true. True or true, that's true. False or false, that's false. False or true, that's true. True or false, that's true. True or true, that's true. Right. Then we've got A implies B and C. So we're looking at A and we're looking at B and C. We're looking at A and we're looking at B and C. So we have true and true implies true, that's true. True implies false, we have got false. True implies false, we have got false. True implies false, that's false. False implies, here we have got a string of false. False implies anything we know that's true, 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 true. Right. Then we look at not B or not C implies not A. So we're saying this implies not A. False implies false, that's true. True implies false, that's false. True implies false, that's false. True implies true, that's true. False implies false, that's true. True implies true, that's true. True implies false, that's false. True implies true, that will be true. Right, so we're looking at not B or not C implies A. Let's start again. True implies true, that's true. True implies true. True implies false, that's false. Then we have got true implies not A. Right, so we are implying not A, so I think I was doing for not C. True implies true, that's true. True implies true, that should be true. Then we've got true implies true, that should also be true. Then we've got true implies not A true, that should be true. Then we've got false implies true, that's also true. I've got true implies not A false, this should be false. So we are here, this should be false. Then true implies not A, that should be false. Then true implies not A, that should also be false. True implies not A, that should be false. False implies false, that should be true. So we should be sitting like this. Right. So then they are saying comparing, we want now the if and only if statement there. So we're going to have a statement that will go and say we have if and only if. Sometimes they can put it in between. If they draw the truth table for you, they can put it in between these two columns, right? So they can put it in between those two columns. So if and only if needs both of these to be true or both to be false. True, true, true. False, false, true. False, false, true. False, false, true. True, true, true. True, true, true. True, true over here is true. True and true is also true. It is also true. So eventually we have a statement that is always true, and that is called a tautology. So it is called a tautology. So we can conclude that the sentence is a tautology. Right. Any questions there? Now, that is a way of representation using a truth table. We also have, so we had this, we did this. We also had the following. Suppose we want to determine if some first order logic sentence built from 3 atomic sentences P, Q, and R is a tautological consequence, right? We build, that is, I think, one more thing that we have not mentioned. And we looked at logical consequence. It only makes sense that we look at tautological consequence. So let's just look at tautological consequence. So when you read, this is what is called tautcon. Right? So there are the shortcuts in the textbook. This will be known as tautcon. Right. So a tautological consequence, right? It says if you've got statements A, B, C, and D, we say the statement, a statement is a tautological consequence, consequence of other statements, When this happens, other statements, when they are true, each time it is true. Right. So logical consequence said whenever these three were all true, the one is also supposed to be true. We say that then D is a logical consequence of A, B, and C. Here we're saying we look at D and say whenever D is true, right? When D is true, then they are supposed to be true. When D is true, the input statements that we are comparing against are all supposed to be true. So it looks starting from the statement itself and says, does it yield in true? Then the remainder also have to be true, right? So every time it is true, the inputs also have to be true. All right. Now, we can also then use this in the question that we're currently having. So sentence the tautological consequence. We then say we have got P, Q, and R. So we want to compare. A tautological consequence is, or a sentence built from P, Q, and R is a tautological consequence of this and that statement. So we've got this and that. So if whatever statement that we need is going to be a tautological consequence, right, of these two statements, we need for it to be true here, right, and then there as well. It needs to be true over here and over there for it to be a tautological consequence. Right. So we then say only entry in line 8 is true. We don't care about line 8. Only entry in line 1 and line 5 is true. We see. And then on entry in line 1 is true, and only entry in line 5 is true. So the only entry in line 1 is, and 5 is true. So the correct option will be option 2. Right. Then we have When we're looking at TOUTCON, right, the only time that we have this to be true, right, is when these are also true. So what we can say about TOUTCON is a sentence is a logical consequence if and only if the inputs to it are also are true, right? We can claim tautological consequence, right? When if we look at the statement, whenever it is true, or it is true if and only if the inputs are true, right? So we can use that in definition, sort of in if and only if. Right? So when all of them are true, then it is also true, and so we say when all of them are true, then it is also true. When it is true, all of them are also true. Right? So you cannot have true or false leading to true, because when you have true, then not all true. And you cannot have false and then have true, because when they are true, it should be true as well. Right. So that is tautological consequence. Then we say, suppose we want to determine if the some first order logic is built from three atomic sentences P, Q, and R is a logical consequence. So logical consequence says if we have these to be true, then this should also be true. Right. So we're going to see the close relation between tautological consequence and logical consequence very soon. Right. So we're going to demonstrate tautological consequence and logical consequence very soon. So TOUTCON says true should lead to true, true should lead to true. So that's LogCon, right? So of the given options, it says line 1 and line 5 should be true, right? Line 1 and line 5 should be true. Of these given options, this is the correct one. Right? Now, this is LogCon and TOUTCON. So I feel I need to make the illustration here. So we have, say, let's call them inputs, and then let's call them outputs. Right. So inputs true, false, false. Outputs true, false, true, false. So we can look at LogCon and we can look at TOUTCON. So logical consequence demands that when the inputs are true, the output should be true as well. So it says this is logical consequence. When the inputs are true and the conclusion is false, it does not follow logical consequence. When the inputs are false, you can have true or false, it is still fine. It is only strict on the inputs being true. We only attribute LogCon when the inputs are true. That's when we follow up on the outputs. TOUTCON looks for when the conclusion is true. Each time the conclusion is true, so we have it over here and over there. So over here it's always when the conclusion is false, we cannot talk of TOUTCON. It does not define TOUTCON. Then whenever this is true, the conclusion is true, the inputs, if they are false, then it does not follow TOUTCON. But if the inputs are true as well, then it follows TOUTCON. Right. So if you want to compare TOUTCON and LogCon, you see that a sentence or say if we have or we can say tautcon implies logicon. Tautcon means logicon. So if a relationship is a tautological consequence, then it also means that it is a logical consequence. So we saw this happening here when the same choice that made the tautological consequence also made it a logical consequence. So this is the relationship between tautological consequence and logical consequence. All right. Let's look at these two. It says, suppose we want to determine whether P or Q or R is tautologically equivalent to Q and R. Right. We build the complete truth table and then compare these two columns for these two sentences. The sentences are tautologically equivalent if Q and R, if all values in both columns are true. That's tautological equivalence. So all values in both columns are true. If the two columns are identical, that's logical equivalence. Then at least one column is a true, that's satisfiability. Right? Then none of the above is none of the above. All right. Then we have this as well. Consider the following first order logic sentence in the joint truth table below. Then write down the number of the option giving the correct interpretation of the truth table. Right. So we want to build up this sentence. Right. P and not Q or R, if and only if P and not Q or R. Right. So we have P and not Q or R, P and not Q or R. The if and only if is going to be, if we have an if and only if in between here, it's going to be true, 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 true. The negation of that is going to be, when we negate that, we're going to have false everywhere, right? So then it means the statement is a contradiction. The statement is a contradiction. Yeah. All right. Any questions? Then lastly, we can talk of not P, R, not R, and Q. And then we are looking at P and Q implies R. So we've got three inputs, P, Q, and R. So we're going to have, let's say 1, 2, 3, 4, 5, 6, 7, 8. Then we're going to have P, Q, R. P, Q, R. And then we're going to have P and Q. And then we're going to have not P, not R. Q we already have, so we're not going to duplicate. And then we're going to have P and Q implies R, like that. Now we have true, 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 false, 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 false. We're true, true, false, false, true, true, false, false, true, false, true, false, true, false, true, false. P and Q, we have true, true, false, false, and then everything is false, so it's going to be false, 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 false. Then node P is going to be false, 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 true, 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 true. Node R is going to be false, true, false, true, false, true, false, true. Then P and Q implies R. True implies true, that's true. True implies false, that's false. False implies true, that's true. False implies anything that's true, so true, 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 true. And so we've got row 1, 2, 3, 4, 5, 6, 7, 8. And let's see if we can find the relationship between tautological equivalence, so between these three and the last one. So can we check for, is it a contradiction? No. Is it a tautology? No. Looking at, is it satisfiable? Yes. So it is satisfiable. Is it a logical consequence? Right. Let's identify when these three are true. We're going to have true over here. We're going to have true. This false and false. No. We want to have true, true and false. No. So false everywhere. True over here. We've got true, true and true. This is the only time that it is true, right? So we've got true, true, and true. We have it as well as true, right? Then that is the only time when this is true and they're also true. So it is also a logical consequence. Is it a tautological consequence? It's true here, but it's not true there. It is not a tautological consequence. So we have it's a logical consequence and it's satisfiable. Like that. So that is the conclusion you can come. Say the fourth sentence is a logical consequence of the first three sentences. Right, any questions? Then we can take a stop there. So let's take a quick 10-minute break, and then when we come back, we should be able to move on and look at validity. All right. So hang on, we come back at 1:30, and then we look at validity.